All right, so let me start from first slide. Right, so this is the third lecture about gravitational waves, gravitational wave theory. And I know there's been already a couple of lectures about the theory of generational gravitational waves. I will recap some concept of it, and I will go a little bit into the interaction between the wave and the detector. And yeah, so this is just a couple of words about me. I'm the one on the right for your information, and I'm a professor of physics at University of Milan Bicocca. And I participate within the LISA consortium and the European and International Pulsar Timing Array. So my expertise lies more in the low frequency part of the gravitational wave spectrum. So as you see from my research interest, I'm interested in gravitational wave sources, especially in the low frequency band. And in particular, most of my work is related to massive black hole binaries, as it will appear clear from my last lecture. So this is the plan, the outline of the 3 lectures I'm gonna give you in these days. So lecture 1 is just essentially setting a bit the stage. So I will recap a little bit about the theory of gravitational wave generation, just giving you some key pointers to what you probably already heard this morning. And I will talk about the formation of gravitational waves from binary system and how we detect these gravitational waves. And in particular, we'll focus mostly on laser interferometry, because I know there will be some nice lecture about pulsar timing by Steve Taylor later on in the week. Then on Thursday morning, I will talk specifically about sources of gravitational wave in the low frequency band, and in particular focusing on LISA. I will talk about stellar mass black holes and MRIs, and in particular the last lecture will be devoted to supermassive black hole binaries. Okay, so let's get started. So this is just a nice picture of a small portion of the universe, where you see few stars and a lot of different galaxies, right? And we've been looking at the universe for many, forever essentially, but in a scientific sense, let's say for many decades with our electromagnetic telescopes. And in fact, we've been quite good at it in recent years, covering the whole electromagnetic spectrum. So this is just a cartoon where I show the electromagnetic spectrum. You see here. You can see my pointer, by the way, right? Yeah. Okay, cool. And you see the 2 windows that we are able to probe from Earth. So that the optical window and the radio frequency window, which will be particularly important for pulsar timing. And since we are essentially blind from the ground to all other wavelengths, we've been quite good in sending up telescopes to probe all the bands of the electromagnetic spectrum. And these gave us an enormous gain in understanding of the processes that are happening within our universe. So just to make the point here, what is shown in this slide is essentially the view of the same galaxy, which should be M82, something like that, and in 6 different bands. Okay, so if you look at the galaxy in optical, you just see this sort of milkish halo, which is all the distribution of stars, and some dust essentially blocking the light coming from the center of the galaxy. But when you look at the galaxy at other wavelengths, you discover a whole bunch of different things going on. So, for example, X-ray is very sensitive to violent and energetic processes such as accretion and formation of jets, for example. And you see all these blue dots here are essentially X-ray binaries within these galaxies. And if you go down in radio, you become particularly sensitive to the radio jets that are emitted at the center of the galaxy that you see here, the 2 lobes, the 20 antipodal lobes here. But if you look in the infrared, now you see essentially the negative of this picture, because the dust that is absorbing the electromagnetic radiation here in optical is re-emitting in the infrared. So you see, by looking at different wavelengths, you discover a lot of things. So for example, here in the optical, you wouldn't guess anything about the X-ray processes, the accretion processes that are ongoing in the galaxy. You wouldn't know anything about the formation of this jet. Okay, and I'm just telling you this because gravitational waves give us a completely new window to explore the universe and make us sensitive to events that we could never see before. So just to the very basic theory of gravitational waves. So we all know that it boils down to solving Einstein equations here in the bottom left. And as you see in the cartoon, the equation tells you something that is conceptually simple when somebody tells you that, but really it took many centuries to get here, right? So you have the Einstein tensor on the left here that defines essentially the geometry of space and time, and the stress energy tensor on the right part of the equation here. So just in short, so essentially the energy, or it describes the matter and energy in your objects here, the two stars orbiting each other, and the metric tensor essentially describes the distortion of space-time that is produced by this stress energy tensor. So in practice, what this equation is telling you is that, as we used to say, is that matter tells space how to bend, and space tells matter how to move. Now, if you take a binary like this, so the two objects are orbiting each other, and as a consequence, also the distortion of the space-time that it produces will move around, and the space, it will wheels around, and this whirling will result in the formation of waves, metric waves of the space-time itself, actually only of the spatial components, that we call gravitational waves. And these are waves that propagate outwards at the speed of light, as we see in this numerical simulation, where you see a binary emerging at the center, and the waves coming out of the binary. So this is just a 2D rendering of the 3D gravitational waves. Okay, this is the way gravitational waves are generated, but to go a little bit more into the actual physics and maths of the problem, so all of these essentially translates into these slides, which I presume is sort of summarizing things that you've seen already this morning. So the easiest way to get to the gravitational wave is essentially to take Einstein equations that I showed you before and just solve them for a small metric perturbation onto h mu nu, onto a flat space-time that is described by the Minkowski tensor here, eta mu nu. And when you actually plug this into Einstein's equation and you simplify, you end up with a wave equation here with the Lambertian of this. Well, this is the reverse traced h mu nu tensor, which is essentially, we can consider it h mu nu essentially. It's equal to essentially the source term t mu nu here. And this is a wave equation, and the solution of this wave equation, not surprisingly, it's a wave, and it's a wave that propagates at the speed of light, and it displays two, at least in general relativity, two independent polarizations, which are called H plus and H cross here. So in the bottom of this slide, you see the metric, the form of the metric tensor for an incoming wave in the x direction. So you have a wave coming in the x direction, and you see that the perturbation is transversal to the propagation of the wave, and this is the same as in electromagnetic waves. So the oscillation of the field is perpendicular to the direction of the wave propagation. And on the left, you see a depiction of the two polarization of the metric, right? The plus polarization and the cross polarization, which are called like they're called for obvious reasons. So when you then want to solve this equation for an actual system, you need to specify this stress energy tensor T mu nu. And it's fairly easy to do so for a binary system where essentially you can just assume that the two objects are point-like objects with mass m. So it's then simple to write down the equations. And what you find, well, actually, even before that passage, what you find is that this perturbation h mu nu is essentially proportional. So you see here some constants, and well, the constant in front of it it's actually quite important and quite scary, because you see it's like 10 to the minus 50, right, in CGS, is inversely proportional to the distance to the source, which is actually expected because it's, for conservation of energy, you have an outgoing wave, so the amplitude of the wave has to be proportional to the inverse of the distance to the source. And the other important thing is it is essentially proportional. It's given by the second derivative of the quadrupole mass moment of the source. Okay, and so this tells you something particularly important. So you have a second derivative of quadrupole mass moment. So it means that to produce gravitational wave, you need a system that is accelerating. So acceleration must be involved, and this get me back to the binary system, because if you have two objects orbiting each other, like in the plot here on the left, so this is a system which experience an acceleration, and so it is a source of gravitational waves. And as I was saying, it's particularly simple actually to assume that these two objects are point-like masses and to work out what the second derivative of the quadrupole mass moment is in this case. And what you get is the formula that I plot here in the center, which gives you the two-way polarization as a function of the parameters of the system. So you see the two polarization H plus and H cross are proportional to the chirp mass, which is a specific combination of the two masses of the object to the 5/3, times frequency of the wave to the 2/3. And there is this this theta dependence, and theta in this slide, it's the inclination of the source with respect to the observer. So usually this in the literature actually is usually called iota. I don't know why it's theta in these slides, but anyway, and here you see what it is, right? It's the direction to the line of sight of the observer, with respect to the orbital angular momentum of the binary. So you see from this formula here, if you see a source edge on, like in this case, okay, this part goes to 0, and you just have the plus polarization of the wave. Whereas if you see the wave face on, like in this other cartoon here, both polarizations have the same amplitude, both are present. So in the edge on case, we say that the wave is linearly polarized. You have like an oscillator that goes forth and back. And in the edge on, in the face on case, the wave is circularly polarized. You have the two polarizations present in the same magnitude. And of course, you have everything in between, right? If you just move away from an edge on source, you will see the cross polarization start to emerge, from the system. Now the binary, the gravitational waves take away energy from the system, and again, it's not too difficult to work out what the energy is, and you might have seen this calculation, I don't know, in the previous lectures, but what you find is that the energy taken away by the system is essentially proportional to this formula here, is given by this formula here. And again, you see this proportionality to the chirp mass to the 10^3 and to the gravitational wave frequency also to the 10^3. It's actually very interesting to look at this thing at the merger, because at the merger of a binary system or at the merger of two black holes, okay, the maximum frequency that is reached by the source is proportional. It's the frequency at the innermost stable circular orbit. Okay, and it's very simple. You can do the calculation in the Newtonian approximation, and it's very simple to see that this frequency is inversely proportional to the mass of the system, which cancels out this chirp mass dependence. So this tells you that it doesn't really matter what is the mass scale of the system. A merging binary will have at the merger a luminosity that is of the order of 10 to the minus 4 c to the 5th power divided by g. And this number is pretty big. It's like 10 to the 56 ergs per second, which, by the way, it's about 10 times the luminosity, the electromagnetic luminosity emitted by the all stars in the universe. So this tells you already that gravitational waves are that carry away a lot of energy, but this lot of energy will produce as we will see, a very small strain, which tells you essentially that space-time, if you have to think as space-time as a medium, this medium is extraordinarily rigid, okay, because such a big injection of energy just produces a very tiny perturbation far away from the source. All right, so we spoke about the two gravitational wave polarization, and here they are in this figure, in this cartoon that shows essentially what is the effect of the wave that is incoming now in the screen, or outcoming is the same thing, and this is the effect on a putative ring of test masses. Okay, so the space oscillates in this quadrupolar fashion, just stretching in one direction and squeezing in the opposite direction. And this, I mean, for a sinusoidal wave, this is of course a periodic pattern. And the cross polarization you see is exactly the same as the plus polarization, but rotated with respect to it by 45 degrees. Okay, so now, as I mentioned before, we have this problem that space-time is extraordinarily rigid, right? And so the amplitude of the waves, as I said before, is proportional to the mass of the system, to this weird combination of the mass of the systems, and to the frequency. Okay, so one can think, and people actually have thought about this in the 50s. You might put on paper a calculation and say, okay, what I would need to produce a gravitational wave that is detectable, and well, you can try to spin a bar of a ton, a bar of 1 meter in size, 1,000 times per second, and still this amplitude gets you to 10 to the minus 35, which is something that, it's hopeless to detect. So in practice, the only viable way to get anything that is borderline detectable is to turn to astrophysical sources, because, if you have very massive objects, this chirp mass gets pretty big. And if your system is compact, this frequency can also be quite high. Okay, so the best candidate for gravitational wave sources are, in fact, compact binary objects of astrophysical origin. And here I just plot a collection of the systems that we are interested in and that we will see during this lecture week. So there would be so the typical sources that we have already seen with ground-based detectors are binaries of black holes and neutron stars. So any combination of those black hole binaries, neutron star binaries, neutron star black hole binaries. But we know there are other, and I know there will be a lot of lectures about those sources and their formation channels, what we've seen with Lagrange, Virgo, and so on and so forth. But also another very interesting source of gravitational wave is related to supermassive black holes. because we gained a lot of evidence in the past 20 to 30 years of the existence of supermassive black holes at the center of essentially each massive galaxy. And those supermassive black holes can be sources of gravitational waves essentially in two main ways. One way is by hosting a small compact object that is orbiting around it. And these are the so-called extreme acceleration spirals that we will see on Thursday morning, or by merging together with another supermassive black hole. And this happens in general following galaxy mergers, because our understanding of the process of galaxy formation is that it proceeds in a hierarchical way, where galaxies merge frequently with each other. And if two galaxies host two massive black holes at their center, the two black holes will eventually form, as we will see on Thursday, a massive black hole binary, which is anticipated to be probably the loudest sources of gravitational waves in the universe. So those are the systems that we are essentially interested in. So just another piece of information about the theory, which again, I presume you might have already seen. Since gravitational waves take away energy from the system, and this energy has to come from somewhere, and it is essentially the binding energy of the binary. So a very cute and simple calculation that one can do is just to work out what is the evolution of a binary system under the emission of gravitational waves. So again, you can take your binary, assuming taking a circular approximation for simplicity, and you can write the energy of the binary as -2 gm mu. Mu is the reduced mass of the system divided by 2a. And then what is the energy that is radiated by the binary, which is the formula that we've seen before, but recasted as a function of the separation instead of frequency by using Kepler's law, essentially. This f of e here is just a correction for binary eccentricity that we can forget for the moment. Okay, then you can simply write a energy balance equation whereby the energy radiated by the binary equals minus the energy change, the internal energy change in the binary, and you can solve for the binary sigma-major axis to get this formula for the E in the T, which first of all tells you that, well, not surprisingly, it's negative, right? So binaries shrink as effect of the emission of gravitational waves, and is proportional to the third power of the mass of the system, and is inversely proportional to the third power of the separation to the system. And this is a very important point, because in order to produce gravitational wave sources, you need the two compact objects to get close together to start with. And this is not trivial. I'm pretty sure there will be a lot of talking about this in the next few lectures, because for stellar black hole binaries, if you just consider the size of two stars when they undergo their giant phase, and if you take that separation and you form two black holes at that separation, you are way too far in order to produce, to merge within an ample time. And the same problem arises for the supermassive black hole binaries I was talking about before, because following galaxy mergers, we will see that it's easy to get the two black holes to, let's say, parsec separation. But at parsec separation, the emission of gravitational waves, even for two very massive black holes, is so inefficient that still the two black holes will not merge within an ample time. So this is something that you will hear a lot about. And again, you can change this amplitude. So here you see actually how the separation goes versus time, right? This a to the -3 function. You can actually now use Kepler's law to turn a separation into a frequency, because I forgot to mention, but presumably you already know that for a circular binary, the frequency emitted by the wave is simply twice the orbital frequency of the system. And you get this formula here for the frequency evolution as a function of time. And here you see it's proportional to the chirp mass to the 5/3 and to the frequency to the 11/3. So first of all, for a given frequency, you see that massive sources live longer. Okay, and this is actually sorry, the other way around, because this is the F in the T. So if you revert this, the T in the F, the time that a source spends at a given frequency is inversely proportional to the mass of the system. So this means that low mass binaries essentially generally live longer, okay, at a given frequency. And we already saw this, for example, with LIGO, right, where the LIGO in vehicle, where the black hole binaries that we observed stay in band essentially for a second, whereas the neutron star binaries can live up to a minute in band. And this will become actually quite important in LISA, because we will see that you can actually set group sources depending on how long they live in band. And of course, you see this frequency proportionality that at low frequency binaries live much longer than at high frequency. And this is why at low frequency you can have an accumulation of sources, and depending on how many sources you have, you might have to treat you might have actually a number of overlapping sources in band at the same time, at which point you're not allowed anymore to think as individual source in your data stream, but you need to consider a superposition of all your binaries, and this will get you in the stochastic background or confusion noise regime. And we will see this will become particularly important again for some sources in the LISA band, and it will be also particularly important for pulsar timing, where the main sources of gravitational, the primary target in terms of gravitational wave sources is expected to be the superposition, the incoherent superposition of a family of supermassive black hole binaries of cosmological origin. Okay, so the F in the T is particularly important because it defines the different regimes of the gravitational wave signal. Okay, so let me just derive this simple, in a very simple manner, the scaling of the amplitude and the frequency of the wave with the parameters of the system. So now the good thing about gravitational waves is that it's actually not hard to get a heuristic understanding of what's happening, because essentially it's a coherent process. Okay, it's not like when you have electromagnetic waves, everything is incoherent and it's a bit more complicated. But if you want to derive the amplitude of a gravitational wave, you can actually do a very, very simple heuristic argument, which I'm going to sketch now. So you have a binary. Let's take two black holes, okay? And the size of the system is the semi-major axis of the binary, or the separation. It's A, okay? A is the separation of the two holes. Now, the gravitation, to a linear order, the gravitational wave will be a perturbation that is of the size of the perturber over the size of the system, right? The size of the perturber is essentially its Schwarzschild radius, okay, in case of a black hole, and the size of the system is A. Now, that perturbation has to propagate from, the source, okay, to the observer, which is U at distance R. So you have this very simple expected scaling for the amplitude. Now, if you just use Kepler's law and you plug in the Schwarzschild radius of a black hole, what you get is this scaling here on the right, which modulo a different combination of masses, you don't have the chirp mass here, and a numerical factor, is exactly what you get by solving Einstein's equations. Okay, so you can use this very simple scaling to get how the amplitude of your wave is going to behave as a function of sources, and also by saying that the maximum wave, the maximum frequency that is produced by your system is the frequency at the innermost stable circular orbit, and this innermost stable circular orbit is essentially a number of spatial radii, right, you can simply find the frequency as this using this formula here, where essentially I just said, okay, the speed at the innermost stable circular orbit is a fraction of the speed of the speed of light, and you know.
Okay, so in case they are late.
Yes. The problem is that, you know, if you are going to being 5 minutes late is not enough.
Martin.
But yeah.
But now it's 20 minutes late.
Yes.
And just to be sure, I ordered it 45 minutes before lunch.
Yeah, I understand.
So
Hey, Martin, I guess you can hear us.
Yeah, we also cannot have the sandwiches yet in our morning.
What's happened?
Probably look another
Martin. Is it? Are you all right? Folks, can I continue, or?
You can continue, Alberto. I think it's okay.
Okay. So were there's a question or a comment, or?
I think we can return to normal now. It's is everything good?
Okay. Yeah, I'm good. I was just wondering whether. Okay, let me just continue here. So you just, you know, I'm just saying that this wave, the black hole that is traveling at you know, a fraction of the speed of light, is gonna, you know, they're gonna go around each other. So the space that they would cover, right, is gonna be like, you know, 2 pi r or some multiple of it, and you can use this to work out what is the maximum frequency of the wave, and you see that this is essentially, you know, several kilohertz in inverse unit of the system mass in solar masses. Okay, so and if you plug in this frequency in here, what you get is that the amplitude of the wave at the maximum frequency the source emits, it's proportional to the mass of the system, and it's inversely proportional to the distance. And those are the scales. Okay, 10 to the 4 Earths and 10 to the minus 20 strain. So perhaps in the interest of time, I'm going to skip the sound, and so you can use these essentially to place your sources onto a frequency amplitude diagram, right? So you see right away that if you have a 10 solar mass black hole binary at say 100 megaparsec, so the typical strain is of the order of 10 to the minus 21, and the frequency is something around you know, hundreds of hertz. But if you move up in mass and you place your source at cosmological distances, this might be 2 black holes in a merging galaxy system, you get a much higher strain, but the frequency is much lower, and so on and so forth. Okay, so now you can take the wave in the frequency domain, which looks pretty much like this, right? You remember the amplitude dependence with the f to the 2/3. So this is a so-called chirp. As time progresses, the source emits at higher frequency and the amplitude increases. You can take this and perform a Fourier transform and move to the frequency space, where essentially the signal look like this. So you have the spiral here, the peak at the merger, and then you have the ring down as the post-merger remnant settles down into a Kerr black hole. Now, so I show that depending on mass, the gravitational wave sources emit at different frequencies, and here it's a panoramic of sources and detectors. Okay, so this is the frequency space from, you know, several kilohertz down to the inverse of the age of the universe, essentially. And on the top, you have a number of gravitational wave sources from compact binary spiral emergers, supermassive black hole binaries, extreme mass ratios spiral, and so on and so forth. And at the bottom, you see different probes that are actually now operational or, scheduled for in future years. So you see ground-based interferometers here in the kilohertz range. LISA, the laser interferometer space antenna, we'll talk about on Thursday at covering the millihertz range, so being sensitive to a bunch of sources here, and pulsar timing arrays that is actually, Steve Taylor will talk about this, and it's sensitive to waves in the nanohertz frequency regime. Going actually farther down in frequency, you can actually detect perhaps gravitational waves from the early universe via CMB polarization experiments, but I will not talk about this in these lectures. Okay, so you can actually produce a slightly different version of this graph, where again there is frequency on the x-axis and characteristic amplitude on the y-axis, and those are pretty much the sensitivities of the three experiments I was mentioning. So you have LIGO Virgo at high frequency here, LISA covering the millihertz frequency regime, and pulsar timing array being sensitive at nanohertz frequencies. So remember the scaling of the frequency with the source mass. So you can populate this diagram with gravitational wave sources. So with LIGO Virgo, we saw black hole binaries, stellar mass objects emitting at frequency of hundreds to hertz or kilohertz. But if I consider different population of sources, I can actually fill this parameter space. So you see again example tracks of neutron star and black hole binaries here, and in the LISA band you have this bonanza of sources where here I just depicted few massive black hole binaries, the signal for few massive black hole binaries, a typical extreme mass ratio spiral here in gold, and all bunch of stellar origin black holes, which by the way might even be multi-band sources, because some of them might actually be observable in the LISA band and just drift to the LIGO Virgo band to merge there. And I will cover this, or I will cover all these sources on Thursday. And moving at even lower frequency, you see what I was mentioning before. So at very low frequency, you have a population of supermassive black hole binaries that are still far away from merger. So they don't evolve, they evolve very slowly in frequency, and they accumulate. So you can see the signal coming from the superimposition of all these sources that produces a confusion noise. And this is what pulsar timing array is seeking to detect. Okay, let me just spend the rest of this lecture talking a little bit about the detection process. And I'm not going to go into too much details. I'm not going to talk about the Bayesian statistics and all this kind of stuff. I'm just going to say some simple things about how the gravitational wave interacts with the detector. So the basic idea was already sketched into the cartoon where I was showing the evolution of the response of a ring of test masses to the incoming wave. Now that ring of test masses can become an interferometer, and here you see a cartoon of what happens. So suppose you have an interferometer where you have an incoming laser. The laser beam is split into two laser beams at the right angle. They bounce, the two beams bounce against the two mirrors, and then they go back, they are recombined, and you read out essentially the superposition of the two beams. Now, suppose there is a gravitational wave coming into the screen. As the gravitational wave stretches one arm and squeezes the other, it creates a dephasing essentially in the two beams. And this is simply because, well, the geodesic along which the photon is changing, but the speed of light remains the speed of light, right? So these, the photons traveling in this arm will take a bit longer to get there than the photon traveling into this arm. And so they will arrive here with a different phase, okay? And this is very simply the detection principle of interferometers. Now, it's a bit more complicated than this, but this is the principle. But in order to derive the proper, the proper response, what you need to do is to transform the gravitational wave from the source reference frame into the detector reference frame, because this is all beautiful, but here I'm always taking a wave that is perpendicular to the detector and oriented with with the right polarization, essentially. And so what one needs to do is essentially to convert the wave that is in the detector frame, which is here depicted by this red basis, okay, into the detector frame. And my detector frame is going to lie in the XY axis, and the two versors that are defining the direction of the two arms are U and V here, okay? So the two waves, what you actually see in the detector, so the actual wave that is produced by the source is a superposition of two wave polarizations. So you have the amplitude of the wave, okay, which is the H plus and H cross that I showed you before. And you have this epsilon, this is the polarization basis tensor of the wave, okay? N and M are the principal axes of the wave. And this tensor defines how the wave is oriented, how a specific polarization is oriented with respect to this with respect to this tensor basis. So you see the plus polarization essentially stretches and squeezes time along the principal axis of the wave, and the cross polarization stretches and squeezes time at a 45-degree angle with respect to the M and M basis. Okay. Now, for a given source, you can always construct this wave base, essentially polarization wave base, and its orientation with respect to the detector frame is defined by a polarization angle, which essentially tells you how the M and M basis is rotated with respect to the projection of the incoming plane of the wave into the detector frame. Okay. Now you see in this slide I actually show 6 different polarizations, and this is because in principle gravitational waves can have up to 6 polarizations. It just turns out in general relativity that only 2 are different than 0, and these are the plus and cross polarization. But in principle, one might have alternative theories of gravities where those other polarization, the vector what's the other one? Tensor, vector, scalar modes of the wave are different than 0. Okay, so one can actually look for this type of waves into the detectors, and if one detects a scalar gravitational waves, it's a big deal. Okay, but in principle, in general, we are only concerned with these 2 plus and cross polarization. So essentially, it's relatively simple. You just have your detector frame, which is defined by the X, Y, Z axis here. U and V are along the X and Y axis. You can express the source frame into the detector frame, okay, by simply rotating along the theta phi axis, defining the direction of the incoming wave, and then perform a rotation along the 2 principal axes of the wave, okay? And this is the passages that you have to perform in order to define what is the projection of this wave here on the top left onto the detector frame. And this is essentially the definition of the antenna beam pattern of the detector. So this is just an example of these patterns for a gravitational wave interferometer. And so the response of the interferometer to an incoming wave is given by the superimposition, is the sum over the two polarization of the wave, of the amplitude of the wave emitted in each polarization, times this antenna beam pattern or response function that you see depends on theta, phi, and psi, okay? The location of the source in the sky compared to the frame of the detector and the polarization angles, okay? So this is how your incoming wave that is given by two polarizations, so it's a tensor perturbation, essentially translates into the detector frame as a scalar quantity, okay? It's just the sum of the two polarization times this frame. So this is just, I mean, I'm not gonna derive any of this. It's pretty tedious, but it's essentially straightforward geometry, if you remember how to do it. So let me just, so you see essentially from here, you can see that if you have for example, a polarization that is aligned with the detector frame, you get the maximum of your response function. So essentially your F is 1, okay? But if you have a perturbation like this and your detector is at 90 degrees with the perturbation, now I didn't put a G, I mean, I couldn't make a G with the detector stretching as the perturbation goes. But you can see already from this cartoon here that at any moment, if you wish, the distortion of the two arms is the same, right? So there is no difference in the time of arrivals of the two arms. So even though both the arms of the detector are perturbed, the perturbation is essentially the same. So when you get to the recombination, you don't see any phase difference. So that's why if you have, for example, a plus polarization like here and a detector that is rotated by 45 degrees with respect to the incoming perturbation, you essentially don't see any effect in your detector. So you see, that's actually, it's interesting, right? Because it's not that the perturbation doesn't perturb the detector, it's just that the perturbation is exactly the same in the two arms. And here is just, you know, to show how a polarization essentially changes the two arms of the detector, the response of the two arms of the detector to a given polarization. In the case they are aligned with the polarization or rotated by 45 degrees. Okay, so we want to see a relative variation of 10 to the minus 22. So we need a log interferometer. So this is just a picture of, I presume this is maybe 1 LIGO. And, you know, it's pretty big. So this is something that I did for a school that was in Pisa. So you can comfortably fit a medium-sized city into a gravitational wave detector, which is few arms, few kilometers long. Okay, so any gravitational wave detector, of course, has its own sensitivity, and the sensitivity is defined by the power spectral density of the detector. And the power spectral density essentially tells you how much noise per unit frequency is in the detector. And this is just the power spectral density of the 2 LIGO detectors during the first observation run. So most notably, you see this steep increase in the noise at low frequency. And this is due essentially to two things. One is seismic noise, and the other is just the inhomogeneity and the variation of the gravitational wave of the Earth gravitational potential on short scales. Okay, so this is why you cannot essentially detect any longer gravitational waves or lower frequency gravitational waves from the ground. Okay, so there is a network of interferometer that is now operational. Well, it's now undergoing upgrades. So we have Virgo in Italy and the 2 LIGO detectors in the US. CGT or Cagra is upcoming. I don't know if it will be already operational in the 4th run, maybe. People there know better than I do. And okay, so this is the detector network that we use to detect gravitational waves. So so you already saw pictures about, oh shit, no. Wait, am I not allowed to skip movies? Yes, I'm allowed to skip movies. So this was just essentially to show the effect of the gravitational wave into the detector, but I'm pretty sure, and this is the chirp of the first gravitational wave source. So I'm just skipping this because I'm pretty sure you've already seen those movies many times. And so this is just as an example, the first gravitational wave that has been detected, GW 15 or 914. And you can see actually here the response, the signal, this h of t, right? The amplitude projected in the detector frame in the Hanford and Livingston detectors. Okay, so let me see. I'm quite late, so let me just see what else I can tell you. Yeah, so this h of t is just the projection of the wave into the detector frame. We want to know how we can extract and what information we can extract from the detection of the gravitational wave. And essentially, the waves depend on the parameters of the sources. The most important ones are masses. And here at the bottom, I show how a gravitational wave changes as the mass change. So you see, the larger is the mass, the lower frequency is the wave. So you see, as the mass is increasing in this cartoon, the wave is stretching out, right? Another important the wave is much more structured, as you see here in the top right, and also if the binary is spinning, this modulation. So how do you detect these things? Essentially, you just do match filter, which is the advanced version of what is doing here. Okay. There is a hand up.
Yes, exactly. Can you hear me, or are we muted?
I can hear you. So.
Oh yeah. Can you hear me now?
Yes.
We just wanted to hear a little bit more about that last slide because there were some internet connectivity issues. So okay. Sorry to ask you to repeat, but I just.
So just these slides I'm on, or wait?
The previous.
So I don't know why I'm having some issues. It appears that I can go forward with my slide, but I cannot go back. Let me just.
The time diode.
It looks like this went forward like that.
Yeah, that's what I think that's what he was saying.
What I will.
Yeah. Oh, that's yeah.
Yeah, let's just start on that slide again.
So this one is fine.
Yeah.
We did not hear this slide.
Oh, you did not hear this.
Yeah, this slide we did not hear.
So if you can go over this one more time. Yeah.
Okay. Can you hear me fine now?
Yeah, there's a little bit of internet connectivity issue, but why don't we try it out?
Okay. Okay. Just let me know if you cannot hear me. Okay.
We'll try.
Yeah.
Yep.
Oh shit. Sorry. You hear that? Okay. So maybe it works. Okay. Hold on a sec. Here.
Yeah.
Okay. Start from this slide. Slideshow. Start from current slide.
Excellent.
Okay.
Oh yeah.
But, yeah, I was just saying that. So the waveform depends on the source parameters, and in particular, one important parameter is the total mass of the system, because as I was mentioning before, the biggest is the mass, the larger is the mass, the lower is the frequency. And here you see how the wave is stretched, so the frequency becomes lower as you increase the total mass of the system. Other important parameters are the eccentricity, because the source is essentially a simple sinusoid if the wave if the binary is circular, but when the binary gets eccentric, you have essentially a more bursty type of emission, because the acceleration is maximum at the periastron passage, and there the wave is much more is much stronger.
Maybe he's automatically calling.
He did say you should let him know.
Yeah,
But how can we?
I think that's the best way.
Maybe switch off the. Yeah, you switch off the video, that might happen.
Yeah.
I don't know what it says.
Yeah, we lost him. Hi, Andrew. How are you? Yeah.
Now I'm back.
Yeah, Alberto, maybe if you switch off your video, it'll help with the bandwidth. I'm not sure.
Yeah, I don't know what's that. Wait a second. I'm just, let me wait. Switch off the video.
We lost you on the spin.
Okay, share screen again.
Yeah.
Share. Okay.
So.
Let's see if I can go back. Oh, I can go back now. Okay, good. So the spin, well, I was just saying that also the spin, have this influence on the modulation of the amplitude, because the plane of the wave, the plane of the source is the plane of the binary is changing in time. So you see the combination of the two polarizations that you see changes in time as well. Okay. So the way we extract this signal from
Didn't you say you have recording sessions?
Sorry.
Didn't you say you have recording lessons of the same lesson?
the data stream that we have, which is the green cube here, with different filters, which are the holes. Okay, but to give a little bit more of a a bit more inside of this, essentially your detector output is given by a noise of your detector plus some signal that of which you know the functional form, but you don't know the parameters. And what you do, you construct a family of filter, and you try to filter the signal with this family of filters to maximize a quantity that is called the SNR, which is essentially matching the signal. It's an inner product between the signal and the data stream, as defined here. So the idea is that when you match the data stream with the template that is actually equal or similar to the signal that is in your data, what you get is a spike there in this SNR quantity, and that defines the fact that, if the spike is high enough, you can say, oh, look, there is a signal in the data with this given parameters. Okay. Now, the signal depends on 17 parameters in the more complicated case, and the idea is that by matching the signal with the template, you can actually define what these 17 parameters are, perhaps not all of them. And you can estimate to some extent what are the errors on those parameters. Now, I understand that given the issues, I ran a little bit late. So can I have other 5 minutes, or should I?
Yeah, we're fine. We started a little bit early, so take your time.
Okay, so parameters that we can measure, just give a couple of examples. So parameters that we can measure are, for example, the position of the source in the sky. and this with ground-based interferometers is done essentially via triangulation, and you know, which is the way your GPS locates you essentially using your phone. For example, an example here was the first detection with LIGO, with the 2 LIGO detectors. In that case, since we had just 2 detectors, right, you cannot play triangulation properly, so you get like these long banana shapes in the sky. So it's very hard, was very hard to localize those sources. However, you could measure many other parameters, and for example, here again from the first detection are the 2 masses and the distance to the source that we were able to extract from the parameters. So let me just conclude by giving just a little bit of information about LISA. So with LISA, actually, sky localization and estimation of some of the parameters of the source might be actually quite a bit better. And the reason for that, so there are 2 reasons for that. One is that LISA, which is like composed by 3 satellites in a triangular configuration like shown here, is essentially equivalent to 2 Michelson interferometers rotated 45 degrees with respect to one to another. And this allows you to disentangle the 2 polarizations of the wave, which helps. So if you disentangle the 2 polarization, you can measure the inclination to the source, and that helps disentangling the inclination from the distance and also from the location in the sky. So that's one thing. And the other thing is that most sources in the LISA band are fairly long-lived, and as they stay in band for a long time and LISA orbits around, because LISA it's orbiting around the sun trailing the Earth, the response of the signal in the detector, the response of the detector to the signal is shaped by the rotation and the motion of the detector itself. And of course, this shaping depends on the orientation of the source in the sky. So as a source in the LISA band stay in band for enough time, so here, for example, I show a massive black hole binary that stays in band for a couple of months, maybe, okay? In a couple of months, the detector moves around, and this time-dependent response of the detector is very effective in locating the source in the sky. And what you see in this plot is an example of a source that, 1 month prior to coalescence is located in the sky with, within few square degrees. But as the detector moves and you also accumulate signal to noise into the detector, you see the sky localization improves dramatically, and it might, in the best cases, become a small fraction of a square degree, which is going to be very important to perform things such as multi-messenger astronomy and other things that I'm going to talk about on Thursday. Okay, so this is all I had for this first lecture. I apologize for the connection issues. I think maybe on Thursday, instead of coming to the office, I will stay at home. Maybe my connection is better, actually. I'm in Italy, so in August, everyone is on holiday, apparently also the internet connection. So, and yeah, so that's all I had for this morning. So I don't know if there is any question now, or if the questions are asked and answered on Slack, just let me know.
Oh, we do have a few questions on Slack, Alberto.
Okay.
I can say them. Or, so I'm not sure. I'll just say them since I'm close to the microphone. The first one is from Moody. Is it Moody? So is there any case where 2 gravitational waves from different sources will meet at the LIGO detector? Do we have to think about that? Is that fair?
So like question is more or less like why LIGO is only detecting one gravitational wave at a time? Like, isn't like a lot of gravitational waves are coming at the same time?
Could you hear that, Alberto?
Yeah, so essentially you're asking about superposition of sources in the LIGO band, essentially.
Right.
Right. So so that's not really that's not anticipated to be really an issue because, well, even with 3G detectors, okay, when our sensitivity will be much better and there would be there might be actually a lot of sources in band, also at the same time, those sources will be, one can actually prove that these sources are different enough that it's not gonna be, in principle, at least, a problem to disentangle them from each other. So essentially, those sources are always gonna be, if you wish, orthogonal in the source parameter space. So as long as you can see, as long as you have enough SNR to dig out the source from the data stream, it's hard to think that you will have this problem in the LIGO-Virgo band. So when we talk about detecting a stochastic background in the LIGO-Virgo band, it's not due to the fact that we cannot disentangle multiple sources, but it's due to the fact that there will be multiple sources in the detector band which are below threshold. So they are not individually observable, but they're essentially the power they produce is actually detectable in the detector. Okay, so you cannot resolve individually the sources, and so, but you can see that there is some extra power that is due to some source to some sources that you cannot see individually. So I don't know if that answers your question.
So, like, just a small question. Till now, do we have any case where two sources are superimposing in LIGO band?
Can you repeat that then?
Has there been any instance of two sources superimposing in the LIGO band to date?
Not to my knowledge, and this because well, we detected about 50 sources and they last in band seconds, right? So it's, you know, we observed for many months, and it's very unlikely that any two of those would happen at the same time. So at least to my knowledge, that it wasn't the case that there were. I mean, there were sources in consecutive days, but not at the same time.
Okay.
Yeah. We have one virtual and one in-person question. Go ahead.
Yeah, very quickly. Was the very first event a very strong or loud exceptional outlier, or were any of the subsequent events as strong as the first one?
Oh, I think there is a lecture about the LIGO detections right afterwards. So I presume there will be somebody that is much more knowledgeable than me to talk about this. But okay, it was exceptionally loud for a first detection, but I think some of the subsequent ones were comparable. I think so. SNR, I mean, in terms of signal to noise ratio, actually, it wasn't the loudest. So, for example, the neutron star binary 170817, in terms of signal to noise ratio, was louder than 150914. It was like SNR of 30, whereas 150914 was 24. It's just that since that one was a neutron star binary, you wouldn't see like a whopping signal lasting few cycles, but it was like a much smaller signal, but with thousands of cycles in band. So the accumulated SNR was in fact higher in that case.
Yeah, this idea of having more cycles again. Great, and I think we'll do one more question from Suvrat, if I'm saying your name correctly. Would you like to ask online? Here, I'll read it. Are we forced to generate a library of templates and do matched filtering for gravitational wave detection? Can we not fit the LIGO data to our model using, say, MCMC and find the posteriors for the unknown fit parameters?
I think there are searches of this type, right?
Yeah.
I mean, where you can just fit a bunch of you just fit a bunch of wavelets and you see whether there is a signal in your data. Yeah, so I think in fact there are searches like this. For example, there are also searches for unmodeled signals. So you just look for bursts of excess power in the data, and this is actually one of the ways the first detection happened. Is that it was so short and loud that it was picked also those pipelines that were looking for unmodeled signals.
Great. Let's just do. There's another one on the Slack. Interesting question. Are LIGO detectors sensitive enough to detect alternate polarizations? So perhaps the tensor scalar modes that you discussed.
Well, the short answer is I have no idea. I can speculate about it. I mean, it all.
Maybe Jonah has some words on it.
I can take a crack at it. So, I mean, the quick answer is it depends how loud these alternate polarizations are, right? And remember, according to general relativity, the answer is 0, right? So there have been attempts to look for these, there have been attempts to look for these alternative polarizations, and they have been constrained.
Okay.
But you know, the question of is it sensitive enough to see them? Well, what's sensitive enough, right? When you're constraining alternative theories of general relativity, it's hard to know,
Right.
you know, what's enough in a sense.
Right.
So the answer is yes and no. So the answer is yes, there are attempts to constrain them, and in principle, LIGO could be sensitive to some of them, particularly the tensor modes.
Yeah, for example, if you have a breathing mode, at what point is that ruled out and just put in the noise category? Or are there searches that allow that to come through?
Yeah, so the scalar mode is hard because we do a poor job measuring the common mode. But there are, I forget how, but there have been attempts to constrain that as well. I think the tensor mode is probably a little bit easier to look for, and there have been attempts, you know, there have been papers taking LIGO observations and trying to constrain the tensor mode, and I think the scalar mode as well. So the answer is yeah, you can put constraints, but of course, we haven't seen it yet.
Yeah. Right.
We don't know how loud those modes are.
Right. Thanks.
I have asked that question. So is it possible by combining several detectors to detect this scalar mode?
Yeah, I think yeah. I close the details, but in general, yes. I mean, in general, yes. Having multiple vectors is very important for measuring polarizations. So yes, I think that's part of the.
And then one more question. Can is for Alberto or can you tell us what are the 17 parameters we talked about? You only gave us that okay, the 17 are the other 11 relevant, or there's then at some point we can tell which are them, but they're not so important.
Sorry, the audio is very disturbed. Can you go to the microphone, or can somebody repeat the question? Sorry.
Did you hear the question?
Yeah, sorry, I was discussing lunch plans with Martin. Could we have a?
What are the other 17 parameters, and are
they relevant for?
Are they relevant? Yeah.
Yeah. What are these other 17 parameters? If you could say something about them, are they relevant? Was the rest of the question?
Yeah. So the 17 parameters are. Well, are listed here more or less. Well, so there are. So of course, so the 17 parameters. So first of all, you can group them into intrinsic and extrinsic parameters. So intrinsic parameters are the parameters that are proper of the binary system itself. So that those are the two masses, the eccentricity. You have the two spin parameters. So those are 6 parameters, right? Because the two spins are 2 vectors. So this gives us 9 parameters. So then there are parameters that are related to where the source is compared to the detector. So is the sky location, the 2 parameters defining the sky location, the inclination, the polarization angle, and then you have, well, if you have eccentricity, you have essentially the line of the ascending node where it is compared to the observer. And what else? Then there is the phase and the phase and the time at merger of the source. So those are, I think I probably and the distance, and those are 17. So for the current gravitational wave detectors, not all of them are measurable. Actually, well, you can essentially measure the masses, the distance. Sometimes the distance is hard because it's degenerate with the inclination. So the signals are actually too short to measure all the spin parameters. So you can only measure combination of the parameters. So for example, you can measure the total spin projected into perpendicular into in the two direction perpendicular and parallel to the plane of the binary. And you're not very sensitive to eccentricity, also because at the very last stage of merger, so the gravitational waves circularize the binary. So most of the binaries in the LIGO band are expected to be circular, although there are channels that predict the existence of binaries with measurable eccentricity in LIGO that has not been measured yet. But yeah, so those are the parameters you can measure at the time. Yeah.
All right, Alberto, thanks so much. That was wonderful, and we'll see you again on Thursday, right?
Yeah, and yeah, I will try to make sure that I have a better connection. Sorry about the problems.
No problem, that was great.
Alberto, I would like to apologize for the glitch with Zoom, and I will now explain why that happened.